Assalamu alaikum. Hope you are doing fine. We know the space around a magnet in which another magnet experiences a force is referred as magnetic field. In this video, we are going to get the expression for magnetic field at a point along the axial line due to a bar magnet. For that, I consider this one as a bar magnet. We know all the magnets provided with the two poles. One is the north pole, another one is the south pole. Actually, they are the ends of a magnet. Then there is one, I take one point here at the center. I call this point as geometrical center of the magnet. When we talk about a magnet, it has got two types of length. If you measure the length of a magnet from this end to this end, we call that length as geometrical length. Clear? If you measure the distance between north pole of the magnet and the south pole of the same magnet, then we call that length as magnetic length. We call that distance as magnetic length. The distance between the edges is referred as geometrical length, and the distance between the poles of the magnet is referred as magnetic length. Clear? Here, usually we use the term, we say that ends of the magnets are called as pole. But practically it is found that the poles are slightly displaced from the ends of a magnet. That is why dots are placed here, slightly away from the ends. So these are the poles of the bar magnet. And here, as the magnets have got two poles, they are otherwise known as magnetic dipole. Here, the word di means two. Di means two. So, bar magnets are otherwise referred as magnetic dipole. Clear? Now, I take one point here along the axial line. What is that axial line? If I draw a line along the axis of the bar magnet, then I call that line as axial line. So this is the axis. If I draw a line along the axis in this manner, then that line is referred as axial line. Now at the axial line, I take one point. I name that point as C. Now at point C, I am going to find out the magnetic field. Okay. For that, I place a unit north pole. I place a unit north pole of magnetic strength QMC. Here at point C, I have placed a unit north pole whose magnetic strength or pole strength is QMC. Pole strength is QMC. Okay, then here in the magnet we have got two poles. Each of them have pole strength equal to QM. QM is the pole strength of north pole and the pole strength of south pole is also taken as Qm. Clear? And the pole strength of this unit north pole is taken as QMC to differentiate this from the remaining. Clear? Now the point C is at a distance of R. The distance of R from the geometrical center of the bar magnet. So here point C is at a distance R from O. Clear? And one thing I forgot to mention, here the distance, the length of the magnet, the magnetic length is nothing but (2L). So the length between north pole and south pole is 2L, means the distance between geometrical center and the south pole will be L. Similarly, the distance between O and the N will remain the same, that is L. Got it? Now I go ahead. Now we know very well, when two magnetic poles are brought close to each other, there exists a force. The force may be attractive or repulsive depending upon the type of poles. Clear? Now here, when we bring like poles, similar poles, here I have north pole. When it is brought near north pole, it will repel. So the force that exists between these two poles is nothing but a repulsive force. And the force that exists between south pole and the unit north pole is nothing but attractive force. Okay, so the repulsive force between north pole and this unit north pole is a repulsive force. It acts away from point C. I take this one as F N vector. This force is Fn vector. It acts away from point C. And the attractive force that exists between point C and S, between different poles, is nothing but an attractive force, that is F vector. This is a repulsive force and this one is an attractive force. So it is acting towards the magnet, and this force acts away from the magnet. Clear? So I am going to find out this force, expression for this force, then I will find out the expression for this force, then I will add them together to get the total force. That will provide me the expression for magnetic field. Let's do that. To get all these things, I will use Coulomb's inverse square law of magnetism. Clear? Now before going ahead, let me provide one information here. I told you earlier, point C we have placed a unit north pole. Okay, this unit north pole have pole strength QMC, which is equal to, here the value of QMC is nothing but 1 ampere meter. Ampere meter is the unit of pole strength. So QMC is nothing but 1 ampere meter. Clear? Okay. Now the force that exists between unit north pole and north pole of this bar magnet is a repulsive force, and it is represented as Fn vector. Fn vector. Okay. Now, this force is obtained with the help of Coulomb's inverse square law. And what does it say? It says that force between two poles of the magnet is directly proportional to the product of magnetic pole strengths and inversely proportional to the square of distance between them. Okay. So it is a mu naught upon 4 pi into the pole strength of this one. I take this one first. Is QM. This pole strength is QM C divided by this one is subscript. Okay, it's divided by the distance between this north pole and point C. What is that? Let me find out the distance. This distance is actually the total distance is R. From that, if I subtract this, I get the distance between N and C. So this distance is nothing but R minus L. Clear? So I take that distance here. I write it here. It's R minus L whole square. And here we know the value of QMC is nothing but 1 ampere meter. So I write that one here. So mu naught upon 4 pi is QM multiplied with 1 divided by R minus L whole square. So the value obtained is nothing but this. Fn vector is equal to mu naught upon 4 pi QM divided by R minus L whole square. This is the value of Fn vector. I take this one as equation number 1. Okay, for my convenience. Then I am going to find out the force Fs vector that acts between point C and S. Okay. So for that also I am going to use Coulomb's law. Okay. Fs vector. This is attractive force and this one is repulsive force. And it is equal to mu naught upon 4 pi. Okay. Then here we have pole strength QM is taken, is multiplied with this pole strength QMC divided by the distance between C and S. What is that? The distance between O and C is R. The distance between O and S is L. So if you add this, you will get the total distance. And it is nothing but, what is that? This distance is R plus L. Now, from the diagram, it is obvious. Okay, fine. That I am going to mention here. So R plus L whole square. So here we know QMC is nothing but 1. So I substitute the value mu naught upon 4 pi QM multiplied with 1 divided by R plus L whole square. So what we obtain is nothing but mu naught divided by 4 pi 1 multiplied with this. If you multiply QM with 1, you get a Q divided by R plus L whole square. And this one is taken as equation number 2. So Fs vector is equal to mu naught upon 4 pi QM upon R plus L whole square. Okay, we have got these two equations. Now, the total force can be obtained if we add these two forces. Total force is taken as F vector. This can be obtained if we add these two forces, Fn vector plus Fs vector. You see that we will do it here. So F vector is equal to, what is this? The final expression, mu naught upon 4 pi Qm divided by R minus L whole square. It is added with this force. Okay. Now here, if you look at this carefully, you will find that here force is a vector quantity. It has got both the magnitude as well direction. But this side, if you see, we do not have any term which represents the direction. So here, let me provide the direction. In what direction Fn vector, the force Fn vector acts? Now it is towards the right side. Now it is along the x-axis. The force is along its x-axis. When the force is taken along x-axis, now we have a unit vector I cap. I cap is used to represent the direction along the x-axis. Whereas this force Fs vector acts in the opposite direction towards the minus x axis. So it is represented by, the direction is represented by unit vector minus I cap. So that I am going to include here to provide the direction. Clear? So here I cap is multiplied with this. This is a unit vector. It's the same thing I do here. So this side it acts in the opposite direction. So it is multiplied with minus I cap. Okay. So this get the minus sign. Your I cap is included here. It is added with this. You got upon 4 pi Qm upon R plus L whole square. Now it's multiplied with minus I cap. Clear? Now, when you multiply this with the plus, minus into plus, it becomes minus. So in the next step, I get this. You know upon 4 pi Qm upon R minus L whole square I cap. Now plus into minus is minus. So minus is written here. You know upon 4 pi Qm upon R plus L whole square into I cap. Clear? Okay. This is the F vector. So here the total force. Now at the beginning I told you the force that a magnet experiences when it is brought near another magnet. We call that force as magnetic field. Clear? So this total force is nothing but the magnetic field. Okay, so what I do, instead of F vector, I write this one as B vector. Here F vector is nothing but B vector, magnetic field. So in the place of F vector, I write B vector. Clear? Then if you look at this term, you may find that here mu naught upon 4 pi multiplied with Qm I cap. Now these terms are common here. Let me mark these things here for your convenience. You see, this term and here also this term. In both the part of the equation, these two terms are common. So it is taken out. mu naught upon 4 pi here Qm is taken out, then a remaining part is kept as such 1 upon r minus l whole square, then minus 1 upon what is left here 1 upon r plus l whole square. Then in both the I is common, so it is written here this manner. I hope I have understood. Then we know that a plus b whole square is equal to a square plus b square plus 2ab. Similarly, a minus b whole square is equal to a square plus b square minus 2ab. Now we are aware of these two formula. Now one more thing is known to us. What is that? It is nothing but this. A plus b whole square multiplied with a minus b whole square equals to a square minus b square to the whole square. Now let me show you how to subtract this part. To subtract this part, I have to take a LCM. Remember this carefully how I do it. I take it as such. B vector is equal to mu naught upon 4 pi Qm. Then remember this. Now if you look at this part of the equation, you will find that the denominators are different. To subtract this, we need to make the denominators equal. So I multiply these two parts. Okay, 1 divided by r minus l whole square. So then here I have 1 upon r plus whole square. Okay, written as such. On the outside, the I cap. Now what I do, I multiply this part with this part, then this part is multiplied with this, right? See, this multiplied with r plus l whole square. Similarly, this part is multiplied with this r minus l whole square. Okay, we know when we make any change to the denominator, we need to make the same changes to numerator as well. So when I multiply the denominator with this part, I need to multiply the numerator with the same term. So this multiplied with r plus l whole square. Similarly, 1 here, this side is multiplied with r minus l whole square. So what I will get if I do so, I get this. Okay. Let me write this one here. Like it is. See, mu naught upon 4 pi Qm. Here, the denominator has become common. So it can be written as this way. I take it common, r minus l whole square plus r plus l whole square. And here we have r plus l whole square minus now as the denominator has become common, we can subtract this minus r minus l whole square. Now see, in the place of this, so if you look at this, it appears similar to this. So in the place of this one, I can write a square minus b square to the whole square. Here in the place of this, I can write r square minus l square to the whole square. Clear? So this can be as mu naught upon 4 pi qm equals to, in the denominator we have r square minus l square to the whole square. Whereas here it is expanded as r square plus l square plus 2rl using this equation. Clear? In a similar way, we have minus. I open the bracket, then I expand this using this equation, right? R square plus L square minus 2RL. Now close the bracket. Now here, I mentioned, forgot to mention I cap here. Okay, the same thing I forgot to mention here as well. I write that I cap here. If I do so, it is not going to make any difference. Okay, right? This is what we have got. Now, here I have a minus, here plus. When this plus multiplied with minus, it becomes minus. Whereas here, minus when multiplied with minus becomes plus. So I expand that. For expansion, I will get this. Okay. Write a I cap outside. Okay. So r square plus l square plus 2rl minus r square then minus l square plus 2rl minus and minus multiplied with each other and get a plus. And we just plus divided by r square minus l square to the whole square. And here I cap. And here, if you look at the diagram carefully, you may find that the value of L is too small compared to R. Clear? So we can say R is very large compared to L. So L square is neglected. So when we neglect this, what happens? R square minus L square to the whole square becomes equal to, when I neglect the L square, I get R square. Only R square is left there. R square to the whole square is equal to R power 4. This is what I am going to use here in the place of this. Got it? Then, now look at here carefully. Then we have plus R square minus R square get cancelled. Similarly, plus L square minus L square get cancelled. Here 2RL and 2RL gets added up. Right? So, in the next step, we get B vector equals to mu naught upon 4 pi into QM. What remains here is 2RL plus 2RL becomes 4RL. Divided by here in the place of this, write R power 4. Then I cap, which is the unit vector and provides the direction. Okay. Then let's see what I do. B vector equals to mu naught upon 4 pi Now, see, I am going to make a small change to this. Here, 4 calculators 2 into 2. Therefore, it is written as 2 into 2 RL divided by R power 4 I cap. Okay. Now, I take a QM inside. So, the multiplication is not going to make any difference if I do so. Mu naught upon 4 pi. I write it like this. 2 multiplied with 2. Here Q is taken inside. Or actually I write like this. 2L QM, then R is written beside it. Okay. Or one more thing I can do. That this R and this get cancelled. It becomes R power 3. Okay. So R do not exist here. So it's R power 3. So down what we have is this R power 3. This I cap. Now we know when the magnetic pole strength is multiplied with the length of the magnet, we get a magnetic dipole moment, which is represented by letter PM. Okay, so we have this. Vector is to mu naught upon 4 pi. 2. Here 2LQM is nothing but PM. So PM stands for magnetic dipole moment divided by R cube multiplied I cap. Okay. Here what did I say? PM is nothing but 2L QM. This is known as, what is this? Magnetic dipole moment. Fine. Okay, then this can be written here as here, this manner. This equation B vector is equal to mu naught upon 4 pi. No, 2 PM multiplied with I cap for R cube. Now we know that PM multiplied with I cap. No, it can be written as PM vector. It's written as PM vector. So this equation can be written as this manner. B vector equals to mu naught upon 4 pi 2 PM vector divided by R cube. This is the final equation that provides us the magnetic field at point C due to this bar magnet. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put your questions in the comment section. Thanks for watching.